So basically, yeah, you learn about power generation, transmission, and distribution in this chapter 1. It's a very introduction slides. Okay, so you have generating stations. Then normally we have a step-up transformer here to step up the voltage. Why do we need to step up the voltage? Anyone? Why do we need to step up the voltage? Go far. Can say so, so that it can go far without the transmission loss. So if you imagine if you have a bucket of water, so you only fill out with half a bucket, then you go to the other side, then maybe only left a few drops. Yeah, to reduce the power loss. So yeah, at least when you transfer to the other end, then there is still something there instead of a negligible amount. Okay, so you step up so that to avoid the power loss, and then you go through this kind of transmission line. Then there is a substation to step down the to step down the voltage, then distribute to the consumers. So it can be high voltage transformer like the factory or the small factory, or then the residential or commercial area. So in a substation, you have a few components. Okay, power line, transformer, disconnect switch, circuit breaker, those things. Then for the generations of electricity, you have a few types of electrical power plant. So normally, there are questions sometimes when you ask, yeah, how do you maintain the almost instantaneous balance between customer requirement and generated power? So what does it mean? What does it mean? So it means, how can you like, for example, if I want to on my aircon, then how can it know that? How can the power plants know that I want to on my aircon, and then can straight away supply me the power instead of ask me to wait for maybe 5 minutes? Then only your aircon can be on. So how can they know that in almost instantaneous, immediately customer requirement? So there must be something, okay, in the systems to do this. So because we can't store the energy, electrical energy cannot be stored. Of course, this is the last time, and now we can store in power bank those things, but still not a big amount of energy. Okay, yeah, still not a big amount of energy that you cannot say you want to store for. But nowadays actually okay already. Like those they store the solar power in the battery and then supply to the whole house during daytime. Yeah, PT equals to PL. 资源 yeah, it shows that you watch the recorded video. Okay, that's good. Yeah, so power balance between generator and load is because of the PT and the PL. Transmit the power and the load. Okay, so there is something to control it. Okay, so power balance, there is a, yeah, they use the hydropower as the example. So water, you should know that hydropower, you will use a dam, right? Okay, then the water behind the dam will flow through the turbine, then the generator will rotate. Then mechanical power, PT, will be generated by the turbine. Then there is a gap, okay? So they will yeah, allows more water to flow through. Okay, the videos of this hydro power station actually is in the extra reading material, so you can watch the video there. So yeah, I don't have. Have you all watched the recorded video? The extra material. So something like this. There is a gate to control the water flow. Okay, so when that detects the load is actually here. The load is actually here. PT equals to PL. Generator is equivalent with this speed, then it will remain constant. So the system is said to be stable. So if PT is less than PL, then the unit will slow down. PT is more than PL, then the generator will speed up. So you will speed up, slow down, speed up, or slow down. Then there is a speed regulator. Okay, speed regulator here to to detect the speed changes. Okay, so if they know that, okay, the governor, that means a speed regulator, begins to act on the weaker gate. Okay, so if the load suddenly increase, the speed will drop. So when the speed drop, then it will quickly bring back to the rated speed. So that's why it is actually, this is how it works. Okay, so you can maintain almost instantaneous power supply. So because of this speed regulator. Okay, any question? So if we look back at there is a extra material here, and then I actually get some hydropower, electrical substation, nuclear power. How do substation works? Okay, so like this hydropower.
Hence up, depending on the amount of drop in elevation, reason behind a turbine at the turbine. It directly produces carbon dioxide of coal lake. Now the water for the hydroelectric plant, but it's more commonly known as a dam.
Yeah, something like this. So there is a gate here. Can you see? There's a gate here. Okay, to control the amount of water to flow inside and then turn the turbine, and later on a generator will generate the electricity. So this gate is open big or small. It depends on the speed regulator to control it. Oh, fish going on. I'm not sure. I don't think so. This is a good question. This is a good question. Perhaps we can. I don't think the fish can go in. Supposedly there should have something to block the fish going in.
Shown on the left side of the diagram.
So I don't want to spend extra time to watch the video with you now, so you can do it later on. So in the extra material here, okay. So then next will be interconnected system. So supposing normally you have one plant, second one, and the third plant, but then in that not individual, they will connect with the tight lines. So we call this interconnected system. Why they need to be interconnected? So these are the advantages. So like why you want to do group assignment. So stability, you have more power. Continuity of service, one of you sick, then the other two can work. Then economic, so it's you can share the cost, so it's more economic. So these kind of questions sometimes will be in final exam. The advantages of interconnected system. Then hydropower stations, you have medium head, high, medium, low head, which is according to the video just now. I off the video. Here. Roughly here. You can see, right? This one, the head. Okay, so there is a high. Can see my arrow, right? Okay, there is high head development, medium or low head development. So there is a formula. So in the video I already mentioned. It's 9.8 QH, but then when you get it, supposedly your unit is already in kilowatt, because this is a shortcut formula. Supposedly the original formula, there is a row water density. So water density is 1000, then they represent with this K. Okay, so you see only 9.8 QH. Q is a water flow rate, H should be head of water. Okay, can you understand? So if you use this formula, then you immediately, after the answer that you get, you need to put in a K, because the original formula is a rho, water density, which stand for this 1000. The head. Okay. Then the makeup of hydropower station is for your info only. Okay. Roughly you have a powerhouse, then theories, those things. Okay, you can watch from the recorded video and extra reading material. Then advantage and disadvantage of hydropower sometimes will be in your exam or test. Thermal, okay, other than If you can understand one of it, then others of the generating power station is roughly the same. So they actually use some way to turn the turbine. So some can use water, some use heat, some use nuclear, what you call, combustion is it? Okay. Then to turn the turbine. So it's different way of turning turbine only. So other than that is actually the operation is roughly the same. Then advantages, disadvantages. Then will be nuclear power station. Atomic fission. Okay, so that to turn the turbine by using the energy released by atomic fission. So then they have different structures. They have reactor, nuclear fuel, and moderator. Those things. And then advantage and disadvantages. That's it for 1A. Then 1B is mostly about very brief info about transmission and distribution. So this is transmission tower. Sometimes we call pylon. Okay. So if you heard people say pylon, then you should know it's actually referred to this transmission tower. Then you have different types of transmission towers in order to support different voltage level. So if normally when we see the big one, will be steel lattice structure that can stand for 500 kilowatt. The one in your housing area perhaps is something like this wooden H frame or something like this. It's only 115 kV. And orange is not so it's like again transmission distribution. Then principle of first. Okay, so power distribution we have transmissions substation and distribution substation. It's just a step up, step down transformer. And this one is actually a step down transformer. Okay, change from medium to low voltage. And interconnected substation means that it's impossible. For example, you want to transmit from KL to Penang. It's impossible. One transmission line then straight away go until there. So it's in the middle. Then something like your rest house. Okay, so you need to have some stop. For it to do power exchange and so on, to increase the stability and so on. And you want to transfer to very far places. Then power distribution, not really, just a theory. Then we have this table. So roughly let you know if it is extra low voltage, we refer to below 50 watt. Low will be 50 to 1K. Medium voltage is actually 1000 to 50 kilowatt, then kV. Then high voltage will be 50 to 230 kV. Then extra high will be more than 230 kV. Of course, a transmission line, okay, you are going to carry the active power from one point to another. So transmission line is important line, because if without a strong transmission line, you can't actually transfer the whatever that you generated to the consumer. Okay, so transmission line, you must be as constant as possible. Losses must be as low as possible. So normally it's capacitor and inductors. So this is the equivalent circuit of the line. You have a capacitor, inductor, and resistor. Yeah, something like this. And the substation equipment. So this is a substation. So sometimes we call TNB house. So a medium voltage substation usually contain the following components. So you have transformer, circuit breaker, horn gate switches, disconnect switches, grounding switches, surge arrestor, current limiting reactors, instrument, transformer, relays, and protecting device inside one TNB house, okay, or substation. Okay, then it further describe all the types of the components that I think already covered in the recorded video, and it's not very important. You can read yourself, right? Any question? Any problem? Then the loads will actually separate into industrial, commercial, and residential loads. So the main thing is that you need to know what is a peak or maximum demand. So maximum demands, it means something like this. When you hit maximum point in a in a in a certain period of a day, then we call this maximum demand. Why is this maximum demand actually is slightly important. The why call pylon? This is a name only. I know. I don't think got any reason. I think just a name. I don't know why they call pylon, but it's really called pylon. Okay. Function of components are not very important. Okay. So okay, common sense things that you need to know. Why is it important for maximum demand? So it's actually like this. Okay, TMP design or supply you the power or cables. Not to say supply, it means design everything. Okay, when you say you want to build a factory, for example, a new factory or a commercial like shopping mall or what. Okay, then the TMP will ask you, okay, how much maximum demand that you want to request? Why they want to know only the maximum demand? Because of what? Anyone can make a guess? The gap need to have a circuit breaker input. That's a cable thinner something. Insulation breakdown. Uh, some of you say cable thinner something. Yes. Cable thinner something. Because when you want to design something, you won't need to know. You don't need to know the average or the low value or low current. You want to know the maximum. So we design for the maximum, right? Because if you can cover the maximum, then you sure can cover the, for example, the protection, everything. You cover for the maximum, then you can cover for the rest, right? So that's why they need to know your maximum demand. So if you give them the wrong maximum demand, for example, I say I want to, maybe I write down. For example, if I say I want to have 100 m, okay, in a month. Okay, for example, I will use 100 m in a month, but then at the end, actually, I only use 80 m. I should write what lah. Okay, I should write what. Okay, I should write what. Okay, so then they will actually penalty. They will give the difference of this means if you can't hit the maximum demand, then you need to pay for the penalty. So you need to pay for the penalty. And this penalty sometimes can cost lots of huge amounts of bill that the company have to pay. So that's why as a electrical consultant, not M I simply right. Okay, supposedly is what or kilowatt hour. Okay, how to know the maximum demand? Oh, that's the thing. So that's why when we, especially a new factory, it's very hard for us to determine the maximum demand. So normally the electrical consultants will crack head for this because you cannot estimate wrongly. If you estimate wrongly, then the later on the client need to pay for the penalty. Jialat already. They will come to you and then ask you, why last time you decreased so high? Then now I need to pay penalty. How to settle? Then we have a lot of you need to do a lot of follow up after the project. Okay. So how to know? Not try. Supposedly they have some process engineer, so they will roughly know about their yes, they are using machines, or then they why they call measure about energy. I recently I managed to to get the energy. I'm literally become energy manager already. I get the license for energy manager. Thank you, thank you. So back to the story. So that's the reason. Then you all need to electrical consultant will need to discuss with the process engineer to know about the process of the factory. Like for example, how many equipments, motors, and all that will be used. That's the thing. Then roughly then they need to calculate as well. Okay, how much they will operate. For example, in 24 hours or maybe 8 hours a day. So then roughly, actually it's roughly also lah. Okay, yeah, estimate the amount for this maximum demand. My worst scope. That one is story after class. Okay, so can you understand this maximum demand now? So it's actually very important, okay, to know the maximum demand. Then we have the load demand curve. And what you need to know now is actually this. Okay, so we have a few types of power stations. So we have base power station, intermediate, and peak power station. So the base power station normally you on the power at all time. That you no need to off the station. Then for the peak generating station means that you only supply the power for this kind of peak. Understand? Okay. So then you need to start quickly, like your car engine. You on it, then you immediately, like this engine, you will immediately start in a few minutes and then immediately supply the power. So we call this a peak generating station. So load factor, not really important. Okay, that's it for chapter 1. Any question? Malaysia mostly, hydro and coal fire. The time before COVID, I think it's 2020 January. We have COVID in lockdown in March 2020, right? Early of 2020, I managed to make a visit to Putrajaya power plant, okay, a factory visit with the students. So let's see if you have the chance to to visit one of the power plants in the future. Then they will explain more. Okay. Maximum demand normally they calculate one time in a month, not a day. Okay? One time in a month. Okay, if you're okay, then we go to tutorial 1. Tutorial 1. In CPG, very easy tutorial 1. Have you done tutorial 1? Okay, perhaps I give you 5 minutes to go through tutorial 1 and I go to have a cup of drink. Yeah, try to do now. Tutorial 1 question, I think 7 questions only. Okay, 5 minutes. Okay, I'm back. Can we start our tutorial discussion? Are you there? Are you all there? Explain the difference. Edin got problem. So Edin, you raise up your hand to answer question 1, is it? So what's your answer? You're here. Explain the difference between base load and the peak load. Okay, answer actually is given in the notes, right? But I show you the answer as well. So supposedly base load, base load has to deliver full power at all time. So that's why you use nuclear or coal-fired stations are particularly well adapted to furnish base demand. Then peak generating plants only deliver for brief interval during the day, so they must put into service very quickly. Consequently, they are equipped with prime movers such as diesel engines, gas turbines, compressed air motors, or pump storage turbines that can be started in a few minutes. Okay, I think should be no questions, right? And question 2, why traditional nuclear power station not suited to supply peak load soon? Because the startup time is the need to use several days to start up, so cannot be used to supply short-term peak power. So you wait until it start, then you already no need the power. Has it got this kind of question one? Oh, may have because I have nothing to ask. It's already it's a too simple subject. That I want to increase the difficulty level also a bit difficult. So sometimes I have this kind of questions. I always need to find a way to pull down the A students' grade for this paper. But that's why I learned smarter already. This round's exam I give some tricky questions so that I no need to spend time to pull down the A grade. Yeah, this round onwards. No problem one, should be okay one. It's still easy to pass. Just that slightly difficult to get A compared to last time. But no problem. See, Ziyuan say can pass already happy. Then you sure very happy. Give the question to your junior. This is a good, uh, yeah, this is a good suggestion. Let me think about it. See, I want to see how many stars I get first. No lah, yeah, roughly the center is there. Last time also got a little bit of tricky questions, but yeah, roughly the same. I will tell you what to do. Never mind. Don't worry. New student? EE student? No, I don't think so. Which chapter susah? Seriously, no chapter is susah one. Oh, okay one. Because I already give a very shortcut way. I mean, straightforward point of way of how to solve the problem. So should not be a problem. Okay. It's not susah, but a bit troublesome. It's a bit troublesome. You need to do a lot, duplicate a lot of work, and I mean a simple thing, but you need to repeat many times. So it's a bit troublesome, but not difficult. May have careless mistake. So a lot of students who can't score A, it is just because of careless mistake. Yeah, that only. Give me 5 star. Yes, thank you. Oh, Laplace, no Laplace this round, no worry. It's very easy chapter. Yes, I say this subject is fundamental, the most fundamental paper for power electrical stream. And that time, actually, this subject actually before that taught by Dr. Yao. Yeah, I got it from him. Then he let me choose one this paper or another subject, power electronics. Then I say, which one easier? Then he said, this one easier, so I take this one. So this is a most fundamental paper, so should be no problem. Complex number, got Got that. You only have to use complex number to solve some calculation. But don't worry about that. We can discuss after that. When I teach you, then we talk about that chapter. You have anything you can't understand, then you ask. Don't drag until the end. Then should not be a problem. Okay. So let's continue. Give two reasons why electric utilities are interconnected. So, where's my answer? This all stability. This this you can get from lecture notes just now. Systems are interconnected have greater service power than the system working alone. It can withstand a large disturbance. Consequently, it is inherent more stable than continuity of service. One breakdown, the other can put into service. Then economic, the load can shed among various generating stations, so the overall cost is minimized. Okay. Okay. Then next we go to next question. Okay. Let's look at this question. So they say the river discharges at a constant rate of 1,003 kilometer cube of water per year. Okay, so it has been proposed to build a series of dams. Okay, where it drops by 100 meter. Okay, calculate the water flow. Can you do it? So this one you have to change from 1,300 kilometer cube per year. Can you change it to meter cube per second? How to change? So it should be 1,300 times 10 to the power of 3, right? Over 10 to the power 3. Because of cube, then you need to have another 3 outside, is it? Yeah. Right. I think so. Then from year to second, how you change? It should be 365 days, right? Times 24 hours times 60 seconds and 60 minutes and 60 seconds, right? So basically, you divide them, then you get this 41.2 times 10 to the power 3 meter cube per second. The power that to be harnessed in megawatts, so you use the power formula, P equals to 9.8 QH. So 9.8 Q will be this value, 41.2 10 to the power 3. Then H will be 100 meter. So when you calculate it, you straight away get from calculator, you get I think 40.4 times 10 to the power of 6. This is a value from calculator. Can see this one 10 to the power 9 should be correct. Okay. Then what I want to, this is a value 40.4 times 10 to the power 6 is a value from calculator. So you straight away need to put a kilo here, watt. So when you change it to megawatt, then you should get this value. You know how to change from kilowatt to megawatt, right? Yes, you have straight away need to put kilo. It is because like I mentioned just now. Okay, I think it's chapter 1A. I mentioned just now, the original formula is actually 9.8 QH rho. So this rho is a water density, so 1,000. So there is a K here, 1,000 here for water density. Water density. Understand that, Going? This is original formula. Don't ask me why. This is not the formula from me. This is the formula from the book, and I also spent some time. Why? Then I searched around. Then only I found the original formula is actually like this, and why they want to put a K. It is because they put a rho here that become K. The story is like this, and this is a formula from book, not from me. I'm not the one who want to make it shortcut. I am just taking the formula from the book, and then I found out this story. Okay, so I let you know. Okay, so that's why calculator values you straight away need to put kilowatt, then change it to megawatt. Yeah, MGH. Yeah, that's right also. Yeah, 我要 MGH MGG is this. 嗯，哦，OK 咯，以后盘来 settle this 啊。Okay, then okay any question? If no question, then we look at question 5. Can anyone know how to do question 5? Anyone? Okay, so they say so. A lot of students can't understand this question. Okay, a modern coal burning thermal station is shown, produce an output of 720 megawatt hour. So calculate the approximate value of the following: the amount of coal consumed tons per day. So if you look at this diagram, it is actually 1 kilogram per second coal and plus with air 10 kilogram per second. Then go through the process that it will produce 12 megawatt. Yeah, it will produce. It will produce 12 megawatt. So now it said it outputs 720 megawatt. And then they ask for the amount of coal consumed per day. So it's supposedly what is the value? Anyone? I really circle the important. Value. So it means what? From 12 megawatt to 720 megawatt, it is actually times 60, right? Times 60. So it means what? How many amount of coal consumed? So it means instead of 1 kg per second, now you also need to times 60, you get 60 kilogram per second. So from this, you need to change it to tons. That one ton per day. Ton per day, yeah, tons per day. So 1 ton will be equal to 907 kg. Okay, so here will be 60 divided by 907. Then second change the day. So you need to 1 over 60 times 60 times 24 hours a day. So you get the answer is 5715 tons a day. Can you understand? Why 60? It is because diagram here 1 plus 10 we will raw material burning, then you are going to produce 12 megawatt of output power. So that's why 12 megawatt times 60, then you get 720 megawatt. Oh, no near to 1000, but so a lot of people say 1000 kg, but the actual value is 907 kg. Google. See, 1 ton to kg, 907. This is a good question. I just follow this one. 1 ton equals to 907 kg. Is it? But normally people will put 1,000. It's actually near to 1,000. Yeah. Okay. But no worry, no worry. This kind of change unit thing is not in your exam. If I want you to change unit, definitely I will give you the value lah. Like 1 ton equals to 907 kg. Are you okay? So no worry about the change unit. Change unit is not in your exam. It's just a question for tutorial 1. If not, then tutorial 1 is too easy. No, this is a question from one book only. Okay, so if I want you to change unit, I will give you this kind of like how many horsepower equals to how many watt. Okay, 1 ton equals how many kg. I will give you this kind of reference value. Okay, Edin, okay? So no worry about the change unit. Okay, but of course, definitely this kind of watt, megawatt, kilowatt thing you have to know lah. Then the second and time day, those. Okay. Oh, okay. No worry about that, Nicholas. Okay, we just use 907 kg here. Okay. So if this kind of question is in the exam or test, I will tell you how many kg that I want. Okay. So in order to reduce confusion. Okay. The amount, okay, question 1A, okay, 5A, okay, right? Then 5B, the amount of smoke gas fly ash released tons per day. So it's actually like this. So you actually 1 kg will produce 10 kg. So means this one needs to times 10 in order to have 17150 tons. Okay. Then they burn and then they release. So the answer is actually like this. Yeah. So okay already. So according to the model, to the A intake is 10 times the core intake. So 157,150 tons per day. So the material intake will be these two raw material burning together, right? Will be these two add together. So out of this intake, so at least the air parts must go up the stack. Can you understand? So they don't have you don't have an exact amount. So because we won't know how many of after you burn, then you may have some dust left inside the boiler, right? Burner here. Okay, so how many will really fly out into the air? We don't know. Okay, so but then we know that the burning it won't exceed the burning materials, right? So that's why they say 62865 tons per day is a material intake. So out of this intake, then at least 57,159 tons per day must go up the step. Any question? Any question? So if no question, no, it's a time to do some survey. Okay, if you don't have any questions so far, then you type 1. If you have any question, then you type 2. No response means you're already out for tea break, is it? Oh, okay. For wing, yeah, always 1, 2, 1, 2, 1. Okay, good to know. Most of you are 1. Okay. Then we continue with this part C. Part C, they ask you the cooling water flowing through the condenser, assuming the rise of 10 degree. Okay, so means so the cooling water is 360. So supposing you need to times with 60. Yeah, so cooling water will be 60 times 360, so you get 21,600 kilogram per second. Then you change it to meter cube per second. 1 meter cube will be 1000 kg, so it will be 21.6 meter cube per second. So again, the question is not from me, the question is from a book. Then that's why I just follow the book. They say 907, then 907. Okay. But no worry. Okay, this one it's just for you to roughly to know what to answer and how to answer only. Okay. In the exam or test, I will definitely give a clear question. Why do we need to times 60 for this? This is the first question that people ask. After so many years, I teach this. Let me see. This is a good question. Let me see. Okay, assuming a rise of temperature of 10 degrees Celsius. No. That this 10 degrees is actually meaningless because they just mentioned this one, T2 minus T1 equals 10 degrees. It's same as this only. So why we need to times 60 is because this diagram is according to so-called scale down already. Then 12 megawatt then means you need to times 60 the scale number in order to hit the 720 megawatt the output power. So that's why if you want 360 kilogram per second cooling water in, that means you have to times 60. So it's just like the scale down diagram, and then it scale up everything to 720 megawatt, so it times 60. 1 kg produce 12 megawatt. Yeah, 1 kg here produce 12 megawatt. 18, is it what you mean? So that's why the solution said so long you need to times 360, and then because 1 meter cube weighs 1000 kg, so this amount will be equivalent to 21.6 meter cube per second. Okay. If you are okay, then we go to this question. Nuclear. So they say the uranium dioxide has a mass of 22.2 kilogram when first inserted into a heavy water reactor. So if it releases an average of 372.5 kilowatts of thermal energy during its 19 months stays in a reactor, calculate the following the amount of heat. So you can use the energy E equals to P power times time, right? So power will be this 372.5 kilowatt times 10 to the power 3. Time will be 19 months. So normally we need to change it to seconds. So 19 divided by 12 months times 365 days times 24 hours times 60 times 60. So energy will be equivalent to 1.86 times 10 to the power 13 joule. Okay, then the reduction in weight of in bundle due to energy release, then you can use E equals to mc squared for nuclear. Then E will be this 1.86 times 10 to the power 13 equals to m. C will be speed of light 10 to the power 8, 3 times 10 to the power 8 power 2. Okay, So like this kind of values I will give you in the exam if I need you to use it. So from here, you are going to get m equals to 0.207 gram. 1 month equals to, can you get the same answer? I think roughly the same. 1 month, boleh lah, roughly the same, right? Okay. Question 7. Annual energy consumptions that having the load. Okay, this one it looks difficult, confusing, but actually okay one. So they say 50% of the annual energy is actually equals to 6 gigawatt. So 58% of the annual energy equals to 6 gigawatt. Then 100. Now I want the 100% of the annual energy equals to how many? So that's why it is actually maybe I call this x. So x will be equals to 100 times 6 gigawatt divided by 58. So we will get 90.6 terawatt hour. Can you understand this? Okay, why we can't use this for D.7 or 1.3? It is because you still have a full block. Okay, this is full block. So we have to use this base load, 58% of the annual energy, okay, which is equal to 6 gigawatt. Can you understand? Then from this 58%, then we can know 100% of annual energy equals to how much watt. So from this we will know. Yeah, where you go now? Yeah, never mind. So it's equal to 90.6 terawatt hour. Can you understand? Then part B. If this energy were consumed at an absolutely uniform rate, what would it be the peak load? Okay, what does it mean? So it means this 90.6 is now like this, right? The shape, okay? So you have something like this, right? But then now they say uniform speed means I don't want the top, I don't want like this, okay? Peak load or peak medium, I want all same. Okay, so when I want all same, that means this peak load here will definitely reduce right now. Okay, this peak load will definitely reduce now. So then they ask you what is this load value? Can you understand? So like average down, then the peak value pull down. So it is basically part B, the peak load will be equals to 90.6 times 10 to the power of 12 divided by 365 days times 24 hours. So which is 10.34 gigawatt. That's it. So that means this point here is 10.34. Instead of just now, I think just now is 15, right? 15 here, right? Okay. So now it put down to 10.34. Means some of them here come here, a few up here, few up here, then everything will be a uniform. So they said they want a uniform rate. Any question? Anyone can understand? Huh? That S760 is what? 100 divided by, is it I wrote something wrong? I wrote something wrong, is it? 100 times with 6 gigawatt divided by 58 is equals to 10 point. Eh? 1 minute, I think I made a mistake. 100%, 100%, 50. Oh, okay. Oh, you need to, yeah. This because this one is in terawatt hour. I forgot to times with, you need to times with 365 times 24 hours. Yeah, the formula for S is missing something. The hour lah, 365 times 24 hours, because it's annual energy. Annual energy, and then they ask for what hour. Understand? Annual energy, yearly energy. So 365 times 24. In order to change it to hour, they say they want terawatt hour. That's why my answer is terawatt hour. Okay? Any problem? No problem. That's good. So if no problem, then we will. What shall we do now? Okay. No, I already planned for you. You want to take a, okay? We can take a break. Then we go to chapter 2. Chapter 2. So I plan to stop after chapter 2 lah. Here off. I already open chapter 2. So chapter 2A and 2B. Yeah, so I plan to go in review chapter 2A and 2B first. Hey, wait. Have you done supposedly you already watched a recorded video for chapter 2 as well, right? Yeah, before that we should discuss the lecture, the Google form for lecture 1. Let's look at the question. To balance the power generated and the load, the PL, PT less than PL, the generating unit needs to slow down or speed up. Slow down, yes. The available hydropower can be calculated. Okay, if Q equals 100, what is your P? Yeah, so you need to put a K, kilowatt. Okay, if not 19,008 watts. From calculator is 9,008, but then because of the formula, the rho, so you need to put kilowatt. So this is to test whether you are concentrate in my recorded video or not. Okay, so which of the following is not the advantage of the interconnected system? Protection is not here. So which of the following is not the advantage of nuclear power plant? So it requires more space. Yeah, it's not the advantageous. Transmission line tower is also called pylon, correct? What substation changes medium voltage to low by step down transformer? Yeah, distribution, because they want to distribute to the clients, they need to step down. According to Suruhan Tenaga, voltage in between 50K and 200K. Yeah, high voltage. Which of the following is not the equipment in the medium voltage substation? None of the above. All is inside the medium voltage substation. What is this? Yeah, substation. I think the diagram is this TNB house. Okay, that's good. No problem for this. But the only problem is only 7 students answer. The other 7, where are you? Lecture 1. Then how about lecture 2? Any one of you already watched a recorded video for lecture 2? And there is an extra power factor note and also the 3-phase extra question. Okay, so you must do it. This one you must do it. This is for extra notes, summary notes. Oh, 2 students. Let's see who are the 2 students. Ki-Woon and Zhen Wai. Very good. Already completed your task. That's good. Okay. Yeah, that's a 3-phase extra questions. You have to do it, and we can discuss next week. Okay, plus with your tutorial 2. Today I'm not going into tutorial 2, so I just plan to discuss this one. The lecture notes for chapter 2A, then 2B, then I end the class. Then supposingly you need to complete your tutorial 2 and the extra 3-phase questions. Then we will discuss, I think we are going to meet again next. We are going to meet again next today, right? Then Monday, next Monday, big 2 Monday. So we are going to discuss the yeah, tutorial 2 and the extra 3-phase questions. Then Wednesday offline recorded video for lecture 3. Okay lah, no problem. Google Meet 2 times. No, because I just found that the big 2 this one supposedly if I want to maintain the class, I want to move the class to the morning, I'm okay. I'm going to leave KL in the afternoon. So do you want to stick back to the plan or move the class to morning, Wednesday morning? Hello? No response mean chin cai. Never mind, I already type like this, then we follow this. It doesn't really make any difference also, right? I just make it to Monday Google Meet, then Chinese New Year memang break, then yeah, then week 4 we meet again. Okay, cool. We follow back this plan. Okay, so now let's go to just a quick one. I just briefly tell you what is the important things in chapter 2. Okay, basically it's something that you again a complex power that you learned before in your circuit analysis. So if it is even in the course, what I want to tell you here. In your circuit, it is a bit different, but I already checked. Both book actually state the different thing. So they are from different book, and in the power book, actually is like this. They state this is Vmax, maximum value. So that's why when you want to write in this kind of phasor formats, right? Because so you need to polar format. Okay, polar format. Okay, so you need to use this 10 divided by 2 to find the RMS value. You can't write 10 angle 30. Last time I say cos. If it is given in cos, then we can take the angle 30, right? If it is sine, then we need to minus 90. If it is sine, we need to minus 90 degree. Still remember this, right? Okay, so cos, for example, 10 cos 2t plus 30, so 30 degree here. But 10, you can't write 10 here. You need to divide by 2. Can you understand? Can Okay, so if this is something different with circuit analysis, and you don't ask me why. I already check circuit analysis book memang right 10, and then power system book right 7.07. So we need to be flexible. Cos and sine have to divide. No. Cos and sine no need. Got memang angle follows saja. 30 degree, then you put 30 degree. If it is sine, then you minus 90 degree. This what the angle part is what we learned before. Just the what we call magnitude here, we need to divide. Transmission line, is it? Not transmission line. This is phasor representation in power system. Okay, how to write in polar and rectangular format. Okay, because from chapter 2 onwards, you are having a lot of this kind of thing. Calculations that we need to write in polar format. So let's see if they give you this 169 0.7 as a amplitude, you need to divide it by 2 in order to get 120. Okay, in this format, cosine normally won't have tangent, cosine format, then only you need to write this. Definitely, if they already give you this format, then you don't divide by 2 again. There are a few situations. If they give you RMS value, never mind, later on in the tutorial, then you will know. Okay, sometimes they, I have the tutorial. This kind, then you need to divide by 2. This kind of question. This one no need to divide already. They already give you in the polar format. Normally this one is already in this one RMS. Already in RMS, then you no need to divide by 2. Can you understand? Question C cannot put here. Later you copy and answer, then you don't want to do. Okay. Question 3. I don't have that. This one only tutorial 1. Yeah. Can you get it? So like this one, 120 already bracket RMS. Normally, I think this also RMS. Okay. So already in RMS, then you no need to divide by 2. You can straight away write like this. Okay. Then rather than this will be R J omega L 1 over J omega C for capacitor, inductor, resistor. Then the RL circuit, this one I think. Then they say average power P we call average power, so equals to half VMRN for resistive circuits. For reactive circuits means capacitor or inductor. Okay, your power is equal to 0 because capacitor and powers are lossless elements and absorb no average power. Okay, so average power not important. Okay, then we have complex power. So complex power will be S equals to VI conjugate, okay, which is actually equals to P plus JQ as well. Okay, so P plus JQ. This is complex power. Are you okay? So from one complex power, we will know the real power P for resistors and reactive power Q for inductors and capacitors. So P is a real or average power. Q is a reactive power or called the quadrature power, which indicate the temperature energy storage rather than the real. Okay, it's actually for capacitor or inductor C or L. So in one power, how can we know whether it is complex power, real power, or reactive power? It depends on the unit. So for complex power, the unit will be VA. Okay, for real power P, the unit will be P, and for Q, the unit will be VAR. Any question? So this is a complex power. So for complex power unit, the magnitude for complex power we call apparent power. Okay, and then the angle of the complex power is actually the power factor angle, so which is theta voltage minus current angle, okay, or cos theta V minus theta I. So leading will be I leads V, lagging means I lags V. So power factor you have leading or lagging. So this is a power factor. So power factor equals to P divided by apparent power as magnitude. Okay, or cos theta V minus theta I. Yeah, you can have low power factor because low power factor, again, the TNB will ask you to pay the penalty because low power factor will cause higher current. If higher current, that means you need to have a bigger size of cable, which is more costly. So have to increase the power factor. So normally in every factory, or there is an incoming power supply there, right? Normally we'll have a power factor regulator, so they will automate the system to increase the power factor. So summary of power factor. Then this is a power triangle. Okay, so from a power triangle, we will know complex power, real power, reactive power, as well as this power angle. So calculation of real and reactive power. So from this, normally I will use this S equals to VI conjugate So you know what is conjugate, right? Conjugate actually nothing like this one. If you don't want to press the conjugate on your calculator, then you can stress this 100 angle 120 times with 10 angle negative 10. So conjugate is actually change the angle here from negative to positive or positive to negative, opposite sign only. Okay. Then power equation, S equals VI conjugate for single phase. For three phase will be S equals to SERT3 VL IL or S times power factor. This is a power system, the power factor corrections. So as I said, when you want to improve the power factor, we can't have low power factor. We need to have higher power factor like 0.7 and above. So you use a capacitor, okay, installed in parallel to the load to increase the power factor. Then this is the end for chapter 2A. Any question? The detailed explanation actually is in the recorded video already. So supposing you need to have a triangle, then power angle triangle, then you have PO, Q, and S. So P is always the same. PO and the P new, P new equals to PO. P is always the same. Okay, but Q and S will be, and power factor will be different. Okay, so from this S equals to 100 kVA. Why I know that VA is S? Okay, why I know that this is 100 is for S is because of the unit. From unit VA, then we know this 100K is for S complex power. Okay, then from this 100K here, and then from this the old power factor here, cos 0.8 equals to 36.9. So we know that it is 36.9 here for the angle. So we know S is equal to 100K angle 36.9. Then use your calculator, change it to rectangular format. So you have P for the real, and imaginary parts will be your Q. So you know the P and the Q value. Okay. So once you know the P and the Q value, actually nothing. Okay, then you have to know the Q value. Okay, then you need to find the new power factor is 18.8. So you draw the new power triangle. So now it's 13.8. P you know already, it's the same as the old one. So can you get the Q new? This is a right angle triangle, so you can use tangent. Tangent theta new equals to Q new over P new. P new PO is the same. Then from here you get Q new value. So you want to know the capacitor will be QO value here, 60 minus Q new value here, Q new value here. Then you get the answer 33.7. Any questions? So power factor correction is something important in this chapter. See, week 1 already give tips. The main thing will be power factor correction. Power angle, power triangle definitely important because you need it in power factor improvement, right? Roughly like this. Any question? So of course this one I touch and go so because I expect you to watch the recorded video The recorded video actually explain everything in details, and never mind. After that we discuss the what we call tutorial questions. Then you will understand more. Okay. Are you okay? Okay. Then the last part will be three phase. So three phase is basically the Y delta thing only. So the main thing will be balanced three phase systems. So balanced three phase means they are 120 apart from each other. You have the same amplitude, same magnitude, but then the angle, BP, same magnitude, just that the angle is 120 degree apart from each other. So we call this three phase. So we have two way. One is clockwise, another one is anti-clockwise. So clockwise we call a positive sequence, anti-clockwise we call negative sequence. So the main thing here is actually Y delta 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 Y connection. So you need to know how to see. Okay, this is Y connection. Okay, so Y connection, the voltage here same as voltage here. So that means if you want to find the if you want to find the line voltage is different line because this is AN. So the line voltage means VAB. So VAB will be equal to 3 VP angle 30 degree. So that's it all. So for current line and actually it's like this. A lot of people confused with three phase. They think three phase is very difficult, but actually it's very easy. So you need to think like this. You have a source, then you have transmission line, then you have load, like that only. So you need to think, it's basically you have only two formula, V or I. So whether you need to use a formula to convert, if not, that means they are the same. Means voltage here, same as voltage here. If not, then you need to use only one formula, one for voltage, one for current. Okay, you need to use a formula to convert. Okay. They don't draw the neutral line. Normally for Y connection, there is a neutral line. Okay. Supposedly they have the neutral line. Okay. So what you need to ask yourself is, normally they will just ask you voltage current here, normally given. Okay, so they will ask you voltage or current here at the load side. Okay, and also the transmission line side only. So you can ask yourself from here to here, you have to drag from source to load. So you can to drag and see whether they are the same or not. If they are the same, then you know what's the meaning of same. So for example, point A and point B, so A point here, B point here. So here also A point, this one also B point. Okay, then they link together. Then you drag like this, drag. Oh, so they are the same point. Understand? They are the same point. It means what? Voltage here and voltage here same. So means you no need to use a formula to convert. You only have one formula to convert. Voltage, this one. VAB equals to 3 VP means VAN angle 30 degree. Okay, VP is VAN. So why they need to use a formula to convert? Can you see? This is AN point, AN point. But then line to line is B point is here. B point is here. So AN value, can you say, is it same as AB value? Different, right? So AN and AB is different. So means you have to use a formula to convert. Like that only. Oh, the extra question, there is a reason. The extra question, not usually there is a reason. Because from another book. And the book is a bit shortcut already. But supposing if they say why there is a neutral line, the extra question actually is not a good the circuit is not a good example. Yeah, but I will explain to you all later on. Okay. Boleh lah. Ada macam-macam type of way they draw the circuit, and that is not a good way to draw. But definitely there is a neutral for YY connection. Okay. So that's the thing. So something like this. Okay, you can go through the like for example okay, they calculate the line current in the YY system. So you have to ask yourself, okay, line current will be, where is the line? Line will be here. So this is a voltage here. AN here. So AN here, will it be the same? Will it be the same as this point and this point? Oh, it's not the same, right? So can you say voltage here? Can you say voltage here same as voltage here? So you need to ask this kind of question. Why this question so weird? This is why. This is also not a good way to draw. This is also a good way to draw. Yeah. Yeah, supposedly it's just supposedly it is actually an N neutral line connect together here. for the YY system. So your VAN, so you can drag on your VAN here is basically same as this this AN. Okay, so your voltage here same as means you want to find the current here, then easy, you can just use this voltage divided by the resistance. So that's the thing that yeah, current equals to voltage divided by the total impedance. That's the thing. So for the delta Y delta, same thing also. You have to see. So now this AN here and this is AB. So definitely it's not the same value, right? Then you same place, right? Then you need to use a formula to convert. So you only have one formula only, same as just now. You only have one formula. Okay. Then current current is the same. Current is not the same. Current here current is not the same, right? You go in here, so they're separate into two, so it's not the same. Then that is a formula for current as well. Formula for current. So I make a star already. Okay, so there's a formula for current. That's it. So you need this side is transmission line. This side is load, source load transmission line. Okay, so you just need to drag and see whether they are the same or not. If they are not the same, then you apply the formula. Then delta connection. So delta voltage here and voltage here, you drag to the other side. AB and AB is same voltage, so means VAB here can apply straight away same value. You no need to apply formula. Okay, but then from this VAB and Z delta, you can know IAB, right? So from IAB, can you find IA? Can, but then it's not the same, right? Because very obvious go in, then separate into two. If same, then it will be like just now the Y system. Y system. Current here and current here is the same. They didn't separate into two branches. Are you okay? So three-phase system actually is not that tough. Okay, you just need to know the main point. Okay, then balance Y delta system. Delta connection. Then example delta Y connection. This is last one, I think, delta Y connection. Okay, so like here, like current is the same, current is the same here, right? But then now AN here, voltage here, and this AB is not the same, so you need to apply formula for voltage to change this AB to AN voltage, like that only. Okay, so from this AN voltage and this impedance, then you will know current IA because they are the same. Okay. Then example, then Y delta transform, this is not important, they transform to Y. That's it. So for chapter 2B is about Y delta connections only, three-phase system. Okay. And then I think I have where's the form? Extra note that I posted in I put it in the lecture 2 as well. So you have power factor, we have leading. So how we know it's leading? So I leads V, or it is capacitive load, or is negative Q, or theta I more than theta V. So you have the Bartlett triangle like this. So if it's lagging, it means I lags V, inductive load, or positive Q, theta V more than theta I. So from this, then you can categorize whether leading or lagging. Then for three-phase, line voltage VAB equals to 3 VAN angle 30 degree. So if it is a delta equals to line current. If it is delta load, then it's equals to a line current. So means, okay, this is not important. What I want to say is you just only have these two formula, one for voltage and one for current. So you drag from source, like what I showed you just now, from source part to the load side, then you see whether they are the same or not. If they are not the same, not the what we call parallel, not parallel, then you have to apply the formula. So like this one, line current equals to sub 3 IAB. IAB means across the source of the load, angle negative 30 degree. So if it is in a Y load, then it is equal to the line current. Okay. Then delta Y load can change your delta divided by 3. You can change your delta load to Y load. And for single phase, 3 S equals to VI conjugate. For 3 phase, the power S equals to 3 VAN IA conjugate. So this is the summary table for chapter 2. Any question? So I just summarize everything. 1, no question. Okay, that's good. So if you don't have any questions, so supposing you can, for those who haven't watched the recorded video for lecture 2, you can watch it and then do tutorial 2 and the extra, the extra three phase question. Extra 3 phase question, extra question, and tutorial 2. So I will meet you all again next Monday and continue our discussion. Okay. If no questions, then I will end the class here. Thank you. Bye.